morning, everyone. I'm going to talk today about how to take advantage of simple physical heat transfer models for fire ecology analysis, and I'm going to focus in tropical ecosystems. It is to be said that this work has been done thanks to the collaboration of our research team, CERTEC from the UPC, with the Environmental Change Institute of the University of Oxford. I will divide my talk into the following sections. First, I'm going to give a brief introduction talking about fire ecology in the tropics. Next, I will explain the main challenges regarding wildfire effects modeling in this type of ecosystems. And following this, I will present our modeling framework, that is our approach to study fire effects with a little bit of physics just in a simple way. And I will illustrate that modeling framework with an experimental study case, and then I will end announcing some concluding remarks and further work. It is already well known that wildfires involve severe consequences worldwide, but today I would like you to bring the attention to the tropics, to that area in here, because it is home to most of the world's biodiversity. Tropical forests, savannas, and grasslands are intensively impacted by fires, with a large number of people affected, also with high economical losses, and also with a huge destruction of untold natural resources. And the thing is that nowadays the wildfire problem in the tropics has been, let's say, poorly addressed, meaning that it has been disregarded actually the role that the fire is playing in this type of ecosystem. So meaning that the whole environmental fire impact is poorly understood. So, but what are we talking about when we are referring to tropical fire ecology? What are the main questions that fire ecologists want to answer? Well, they want to know the main physiological and morphological traits that are involved in fire vulnerability, that is how and why plants die, in fire resilience, that is how and why plants recover, and also in fire resistance, that is how and why plants survive, and also all the processes involved in these three main aspects. And the effects of the fire actually depend on the intensity, the duration, and the extension of the fire, as well as on the fire season and on the fire frequency. So it turns out that to answer those previous questions, we have to integrate the biological characteristics with the fire environment, and also with the heat transfer mechanisms that couple the fire physics with actually the biota. And to our opinion, this last aspect has been poorly addressed for the, let's say, fire ecologist community. And as stated by Johnson and Miyanishi, the processes of combustion and heat transfer lie at the heart of fire ecology. So meaning that within scientifically based fire ecology studies, they would become a little bit better if more physics would be involved. So that's our point here. But I admit that this is not an easy thing to do, and there are many reasons for that. There are different sorts of challenges and difficulties when you are trying to model fire effects, particularly in tropical ecosystems. First of all, due to the intense experimental work that fire ecologists have to do, also because the difficulties in terms of the availability of fire monitoring technology, particularly in certain remote areas, and also because heat transfer processes are really complex, as we have already stated this morning. But if we have a look at the different fire scenarios in which fire ecologists work, which can be uncontrolled wildfires and also research or prescribed burnings and laboratory fires, we might find some chances, some opportunities to fill the gap between the fire physics and the fire ecology, that is between both communities. And this is what we have started to do so with the University of Oxford, and we have started working with laboratory fires, because these are the experimental setups that are with the highest degree of control. So let's have a look at our envisaged modeling framework. We want to make a step forward from the statistical relations that fire ecologists usually came up with, in which they linked some simple fire variables like maximum temperatures or heat dosages with the fire effects. So we want to make that step forward and come up with physically based analysis in which, with a little bit of more effort regarding experimental data gathering, both in terms of fire characteristics and also biotic variables. And with simple heat transfer models, we will be able to explain the fire effects with some sort of fire physical arguments. And there is the challenge. Our challenge in here is to use simple heat transfer calculations, just putting the right amount of physics, so just to make our approach still appealing for fire ecologists, and also to set up this modeling framework with reasonably simple experimental setups just for tight sort of budgets. So that's what we are trying to develop. We have started doing so. And that modeling framework has been relying in some experimental data, which has become our work in progress. We are just starting this line now, so it has become our work in progress study case. So let's move on to this. Our study case is what we call the greenhouse experiments, which were part of an European project whose main aim was to study, to understand the role of fire in tropical forest savanna transitions in some sites of Brazil and Africa. So within that project, we wanted to design some fire experiments to apply fire treatments on 27 African species, which were nursed in greenhouses like those one in here at the Wageningen University in the Netherlands. So we wanted realistic fires with a high degree of control, and actually that is what we did. One experiment would consist of the simulation of the fire spreading through the savanna, which was simulated with that Excelsior fuel sort of type that would be placed on top of above the ground, simulating the grassy fuels just coming above the tropical settlings. And in every experiment, we would use seven different tropical settlings. So we would ignite the fire, and then we would monitor the temperature time evolution with thermocouples at two different levels, at one third of the flame height and at 2/3 of the flame height. And 50 seconds after ignition, we would put out the fire by suffocation, by mechanical means, mainly with sand. And because we thought that 50 seconds would be a reasonable residence time for this type of savanna fires. And then after the fire, we would monitor fire effects. As a whole, we did 6 experimental blocks with 7 fires in each, meaning that around 300 individuals were impacted by the fire. So that is pretty much how our experiments looked like. We had about 50 centimeters flame heights, meaning low intensity fires, and those are the typical curves that we would obtain with our thermocouples. We have to say that during the whole experimental set, we had pretty much the same flame geometry and the same temperature time evolutions, so which is actually good, which is actually what we needed. We just wanted the same type of fire impact for every sort of plant. Okay, so with that, let's present our heat transfer modeling approach, which is going to be a very simple approach, but just to show how we can understand the fire impact with through a settling stem. So if we want to keep it simple, we're going to have like very simple assumptions, which are going to be the following. First, we're going to consider our elements as thermally thick, meaning that the external thermal resistance is low compared to the internal thermal resistance. And this is, according to Ben Kusas et al., it is a reasonable approach for wildfire scenarios. Then we're going to consider convective heating transfer tending to infinite, and basically, which means that the external temperature of the stem will be always as the fire temperature, which is impinging the stem. And then we're going to use just a second Fourier law for transient conduction. And we are just going to consider that issue. We are not going to consider any other heat sources or heat losses. It is just an academic example. We want to keep it simple. We want to show the fire ecologists the potential of this type of simple tools. So what we're going to do now is just to show you the pre-processing job that we've been doing, and also how we have been resolving this simple heat transfer model using 2 very popular engineering tools, which are very simple, which are the Haze charts and also the methods of lines analysis. So that is our pre-processing job. According to the first experimental block, we come up with mean temperature time evolution of the 1/3 thermocouples that we were using, and so we have been able to fit a polynomial curve for this temperature time evolution. And with that curve, we have calculated the mean temperature of the first 90 seconds, which is going to be our, let's say, our fire impact in our stems, which has been around 280 degrees Celsius. We have calculated the maximum temperature, which is around 525 degrees, and the ambient temperature for this experimental block was around 17 degrees. And regarding biotic variables, so we have initially considered like a typical stem that we had, for instance, a stem with a diameter of 1.5 centimeters, and then we have considered a typical constant value of thermal diffusivity for wood. Okay, so how can we work with the Haze-Lur charts-based analysis? What can this technique provide us? Well, if we want to apply this Haze-Lur chart analysis, we have to first consider boundary and initial conditions constant and homogeneous, meaning that we're going to consider a constant mean value for the fire temperature, right? So what the Haze-Lur chart analysis can provide us is just a very easy way, just using this sort of chart, to relate the internal temperature of the stem at the center of the stem with the temperature of the fire and with the duration of the fire. So meaning that with this simple analysis, we can answer questions like, for instance, what are the effect of heat doses, or what are the mean fire conditions to get critical temperatures, like, for instance, the 65 threshold for necrosis of plant cells, right? So with this analysis, for example, we can observe how for a particular dose, which might be just like half of dose of our experiments, because we had that mean temperature, that mean external temperature with pretty much half the period of our heating. We're going to have temperatures. We're going to have temperatures in the center of the stem above our critical threshold for plant necrosis. But interestingly enough, with the same dose but with different conditions, we're going to have different temperature, meaning different fire impact. And this, in our opinion, is a very important message for fire ecologists, because they use the dose as a predictor variable for fire effects. And we can observe here that for identical doses, we might find different fire impacts because we are generating different temperatures inside the stem. So that's an important message that can come out in a simple way with this sort of analysis. And also we can see that doubling that heat dosage, it doesn't imply necessarily that we're going to have the double the temperature with half of the dose. So again, that's a warning for these dose parameters that fire ecologists are used to use. Also, other messages that can be found with the Haze-Lur chart can be easily observed with simple sensitivity analysis. And what comes out from this analysis is that, for instance, if we are programming our experiments, if we are analyzing our experiments, it is actually not really important if we pick up really precisely the ambient temperature or even the diffusivity, meaning that if we are having a plus minus 10% of error, that's totally okay. But it's not the same if we are not being precise with the radius or with the external temperatures, because the internal temperature is really sensitive to those parameters. So again, an important message here for fire ecology studies is that maybe mean temperature or maximum temperatures might not be very good indicators for fire effects, just because the external temperature is a very sensible input when trying to explain the fire impact, when trying to explain the internal temperature. But fortunately, we can improve that if we follow another easy methodology, but now a numerical approach with this method of lines. What we are doing here, it is also a very easy and simple numerical approach, but what we are doing here is we are being able to pick that temperature time evolution that we have come up with in our experiments, and we are considering that the external temperature of the stem is actually having the same temperature of the fire, meaning that it's having that temperature time evolution. And what we are doing with this method of lines is resolving the heat transfer equation in different planes of our stem. In this case, we have divided our stem with 6 planes, and we have resolved in every single plane that heat transfer equation. And with this type of analysis, we can have information like, for instance, that one in which we can see the temperature evolution at the different stem depths. So we can easily see how at the center of the stem we might find our necrosis threshold at around 50 seconds. So that's one of the easiest ways to understand that method of lines approach. And also we can have information like, for instance, the temperature evolution at different depths at a certain period. In this graph, we can see that after 90 seconds, which is the whole heating period of our experiment, a stem of 1.5 centimeters diameter would still have maximum temperatures of 170 degrees at 3 mils from the stem center. So I'm just going to leave you with that, just after summarizing some conclusions that might be just the following, that there is a gap between the fire ecology and the fire physics community that can be easily bridged in control experiments environments, and just by using easy heat transfer modeling approaches that even they are full of assumptions and they have full of simplifications, they can help us to understand how the fire impact works in plants, and more interestingly, they can provide us with warnings when we are using heat dosages or mean and maximum temperatures as predictors of fire effects. So just to summarize, our future work will be to analyze the whole experimental blocks and also to cross this data with the observation of fire effects that we have been doing during experiments. And to improve modeling, we are going to try to consider whether or not radiation could be convenient to put it in that model. And also we're going to think about putting some sort of moisture evaporation model in here. And of course, we're going to be looking deeper into the thermal diffusivity characterization, but always just keeping it calm and keeping it as simple as possible. Right, that's all for now. Thanks for your attention. I'm happy to answer any questions.